In today's video, we're going to look at 3 examples of how you would see these problems on a free response section of the AP test. Notice that this is number 5. These questions are not typically in the calculator allowed section because there's not much that they want you to do with the calculator. So most of it is work that they want to see written out by hand. It says, consider the differential equation dy dx equals x plus 1 over y. Part A, and this is actually a complete free response question. This would be worth 9 points. It says part A, on the axes provided, sketch a slope field for the given differential equation at the 12 points indicated, and for -1 less than x less than 1, sketch the solution curve that passes through the point 0, -1. So first things first, to create a slope field, we're going to plug in these 12 points. Here's 6 down here at the bottom, and there's 6 up here at the top. We're going to plug them in here to see what we get, and then we're going to draw our little slopes. So if it's okay with you, I'm not going to create a little chart. I'm just going to verbally say them, and then we'll draw our slopes as we go. So this is the point -1, -2 for x and y. If I plug in -1 to the top, I get -1 plus 1 to be 0. 0 over -2 is still 0. So I have a slope equal to 0 right here. All of these at -1, by the way, are going to make the numerator equal 0. So this one as well, if I plug in -1 here, -1 plus 1 is going to be 0. So all these are going to have a slope of 0. All right, let's look at the next one. -2. So this is the point 0, -2. So if I plug in 0 for x and -2 for y, I get 0 plus 1, which is 1 over -2. That's 1 over -2, or -1/2. If I plug in 0, -1, that will be 1 over -1, so that's -1. If I plug in 0, 1, that would be 1 over 1, which is +1. If I plug in 0, 2, that will be 1 over 2, which is 1/2. Now, by the way, how they grade these is that they typically look for positive versus negative slopes and 0 slopes. So they'll usually give you like a point for having all the 0 slopes correct. And then the other ones, as long as they're positive versus negative, and as long as your 1/2s look a little less steep than your 1s, that's fine. They're not going to be grading for anything more than that. This point over here is the point 1, -2. So 1 plus 1 on the top would give me 2. 2 over -2 is -1. This is the point 1, -1. So that's 1 plus 1 is 2. 2 over -1 is -2. So a little steeper. This is the point 1, 1. That would be 2 over 1, which is 2. And this is the point 1, 2. So 2 over 2, which is 1. All right, so that's part A. Oh, not done actually, just the slope field part. It says to sketch the solution curve that passes through the point 0, -1. So 0, -1 is right here. And again, they just kind of want you to follow along with the lines. So notice that this one is kind of shooting you down this way, and then it's following it that way. And then after that, you can kind of see that when you come up this way, it gets you close to a slope of 0. All right, and then from there, it's not super clear on what happens to it after that. But the good news is they don't actually need us to go much past that because they only want from -1 to 1. So is it kind of like one of those things where it goes flat and then it keeps going up, or does it go down? We'd have to know more about the slope fields over here. And then also, not that they asked us to find them, but all these points right here are undefined. So does it come here and then go up and follow that? We would need more information to find that. So I'm actually going to say, why don't we just stop it at -1? And we'll say it goes to there. And that's as much as we can tell. We don't know what happens after it gets to there. We just know that it kind of comes to there and then stops. All right. Part B says, while the slope field in part A is drawn at only 12 points, it is defined at every point in the xy plane where y doesn't equal 0. It says describe all the points in the xy plane for which the derivative is equal to -1. So if we look here, all the derivatives here were equal to 0. The derivatives up here were positive. This was -2, this was -1/2, but these two had slopes of -1. So if I want to know where my derivative is equal to -1, this is probably a pretty good indication of where it's equal to -1. So notice that this is actually a straight line. It's going to follow all these points. So we just need to be able to write an equation for this line that hits all these points that are going to have a slope of -1. And so the y-intercept is -1, and my slope is down 1 over 1. So the equation of a line with a y-intercept of -1 that has a slope of down 1 over 1 would be negative x minus 1. So all the points that satisfy this line, that lie on this line, except for where y equals 0, are going to have a slope of negative 1. So we've already shown these two. Let's show another one. Let's say if we look at x equals 2. If we look at x equals 2, this would be negative 2 minus 1, which is negative 3. If I plug in negative 2 here, excuse me, I wouldn't want to plug in negative 2 here, sorry. So if I plug in 2 here, I get negative 2 minus 1, which is 3. So I'm plugging in x equals 2. So if I plug in x equals 2, I get 2 plus 1, which is 3, over the y value I just calculated, which was negative 3. 3 over negative 3 is negative 1. So yes, that next point down would also have a slope of negative 1. And you can keep going. If you plug in 3, you get negative 3 minus 1 is negative 4. If I plug in 3 here, I get 3 plus 1 is 4. 4 over negative 4 is negative 1. It also works going back this way. Not here at negative 1 because that's where y equals 0, but let's say at negative 2, for example. If I plug in negative 2 here, that gives me negative negative 2, which is positive 2, and then 2 minus 1, which is 1. So if I plug in negative 2 plus 1 on the top, I get negative 1 over that y value I just calculated, which was 1. Negative 1 over 1 is also 1. So these are all the points in the xy plane that have a derivative equal to negative 1. And I hope, by the way, it makes sense to you, because if you take the derivative of this function, the derivative of y is dy dx, the derivative of negative x is negative 1, and the derivative of negative 1 is 0. So hopefully it makes sense to you as to why these are all the points in the xy plane that have this derivative equal to negative 1. All right, excuse me. Last but not least, part C, which is the big kahuna. This is where we get most of our points from. It says to find the particular solution given the initial condition that f of 0 equals negative 2. So remember the steps from what we did yesterday. First step is to separate the variables. So I'm going to do that by multiplying the y over to the left-hand side and multiplying dx over to the right-hand side. So this is y dy equals x plus 1 dx. Step 2 is to integrate both sides. So that will be y squared over 2 is equal to x squared over 2 plus x plus c. Then use the initial condition to solve for c. So if I plug in 0 for x and negative 2 for y, I get negative 2 squared over 2 plus, if I plug in 0, that's 0 plus 0 plus c. That means that c is equal to negative 2 squared, which is 4, 4 over 2, which is 2. So I'm going to plug that back in there. So we have y squared over 2 is equal to x squared over 2 plus x plus 2. If I want to solve for y, I want to multiply the 2 over to the left-hand side. So I'm going to multiply everything by 2. So when I do that, this is going to become 2x squared over 2, which is just x squared. Then plus 2x, and then plus 4. Notice, by the way, if I would have kept it as c, like if I would have solved for y at this point, and then I multiplied 2 over, before I told you guys that you didn't need to multiply c by 2, because a constant times a constant is still another constant. And that's true if you're going to wait till the end to evaluate your initial condition, but as soon as you evaluate your initial condition, now of course everything is affected by whatever you do. So that's why my 2 got multiplied by 2, because it will change the value there. Alright, and then square root both sides. So y equals plus or minus the square root of x squared plus 2x plus 4. And then remember, we don't want to keep the plus and minus because I want my initial condition to give me this back. So if I plug in 0 for x, let's see what happens. If I plug in 0 plus 4, this simplifies to 4. The square root of 4 is 2, but I want it to be a negative 2, so that means I should keep the negative square root. So my final answer is y equals the negative square root of x squared plus 2x plus 4. Final answer. And like I said, that is a full free response question. You get 9 points for answering all of those things correctly. Alright, let's try this one. It says, consider the differential equation dy dx equals y squared over x minus 1. On the axes provided, sketch a slope field for the given differential equation at the 6 points. So notice that they have 6 points indicated for us here. So let's plug in 0 first. 0, 0 would be 0 on top, and then 0 minus 1 on the bottom. So this would be 0 over negative 1, which is 0. So this has a slope of 0. In fact, wherever y is equal to 0, the top will equal 0, therefore my derivative will equal 0. So here and here, we also have slopes of 0. Over here, we have the point 2 comma 0. So if I plug in 2 down here, oh, I'm sorry, that's a mistake. Those are not 0. This one is. That's my bad. That's where y equals 0, not up here. This is the point 0 comma 1. So if I plug in 0 for x and 1 for y, that would be 1 squared on top, which is 1, over 0 minus 1, which is negative 1. So 1 over negative 1 is negative 1. 0 comma 2 would be 2 squared on top, which is 4. 4 over negative 1 would be negative 4, so that's a pretty steep line. Then over here we have 2 comma 1. So if I plug in 2 on the bottom and 1 on the top, I get 1 squared is 1. And then on the bottom I have 2 minus 1, which is 1. So 1 over 1 is a positive 1. And if I plug in 2 comma 2, I get 2 squared on the top, which is 4. And then on the bottom, 2 minus 1 is 1. So 4 over 1 is 4. All right, there's part A. Part B says, let f of x, y equal f of x be the particular solution to the differential equation with the initial condition f of 2 equals 3. Write an equation for the tangent line to the graph of f of x at x equals 2, and use your equation to approximate f of 2.1. So remember that a tangent line, we need two things. To write the equation of a tangent line, we need a slope, and we need a point. And they are giving us a point. The point they're giving us is 2 comma 3. The slope we can calculate because we are given the derivative right here. So if I plug in 2 comma 3, 2 for x and 3 for y, I get 3 squared on top, which is 9, and on the bottom 2 minus 1, which is 1. So 9 over 1 is 9. My slope is 9. So to write the equation of the tangent line, it would be y minus y1 equals m times x minus x1. And then in order to approximate f of 2.1, I would just plug in 2.1 for x. So there's my first part of my answer. I would plug in 2.1 for x, and I would get y minus 3 equals 9 times 2.1 minus 2. Well, 2.1 minus 2 is equal to 0.1. And 9 times 0.1 is 0.9. And if I add 3 to that, I get that y is equal to 0.9 plus 3, which is 3.9. So there's the second half of that answer. Part C says to find the particular solution to the given differential equation with the initial condition that f of 2 equals 3. So now let's go ahead and solve this. The first thing I want to do is I want to separate these variables. So I'm going to leave my x minus 1 over here on this side, and it's going to stay in the bottom of the fraction. However, I'm going to divide y squared over to the left-hand side. So if I divide it over, I'm going to get 1 over y squared. And I'm going to multiply dx over to the right-hand side. So I have it over here. So I have 1 over y squared, since I had to divide by y squared. dy is equal to 1 over x minus 1 dx. Step 2, integrate both sides. Y squared, if I rewrite that, remember that's y to the negative 2. So the integral of y to the negative 2 is y to the negative 1 over negative 1. The integral of 1 over x minus 1, technically it's a u substitution. So let me show the work for the u substitution over here. If we say that u is equal to x minus 1, du would be equal to 1. So if I do my substitutions, this is essentially u. So it's 1 over u. The integral of 1 over u is ln of u. And if I replace back with what it equals again, ln of u would be ln of x minus 1. So I'm just going to rewrite that as ln of the absolute value of x minus 1 plus c. And again, if you don't believe that, just plug in or find the derivative of this to verify that it goes back to what that is. Alright, if I want to look for my c value now, I'm going to plug in the point 2 comma 3. So everywhere I see an x, I'm going to plug in 2. Everywhere I see a y, I'm going to plug in 3. So this is negative 3 to the negative 1 equals ln of 2 minus 1 plus c. Well, ln of 2 minus 1 is ln of 1, and ln of 1 is 0. So this is 0. So c is equal to negative 1/3, because I can rewrite that back in the bottom of the fraction. All right, let's plug that in here. And then I'm going to erase this just so I have a little bit extra room. So we have, I'm going to rewrite this. Instead of writing it as y to the negative 1 over negative 1, I'm going to write it as negative 1 over y equals ln of the absolute value of x minus 1 minus 1/3. If I want to get rid of that negative, I can divide it over to the other side. So I have 1 over y is equal to negative ln of the absolute value of x minus 1 minus 1/3. And if I want to remember to get y out of the denominator, I can take the reciprocal of both sides. So I can say y is equal to 1 over, oops, this should change to a plus, shouldn't it? That's my bad. That should change to a plus because when I get rid of the negative on this side, this becomes negative and this becomes positive. So it's 1 over that entire thing, ln of the absolute value of x minus 1 plus 1/3. And that is my particular solution to this differential equation. Perfect. Sorry, it's kind of hidden down there, but you get the point. Y equals 1 over the absolute value of negative, I keep forgetting those negatives, sorry, that's a negative. Y equals 1 over the negative natural log of absolute value of x minus 1 plus 1/3. I think I did that correctly now. All right, here's the last one we're going to do today. It says, consider the differential equation dy dx equals 3 minus y cosine of x. Let y equal f of x be the particular solution to the differential equation with the initial condition that f of 0 equals 1. The function f is defined for all real numbers. It says a portion of the slope field for the differential equation is given below, over here. Sketch the solution curve through the point 0, 1. So notice that they actually did all the slopes for you. That would have been so much work to have to calculate all those slopes. So they want us to sketch the solution curve through 0 and then negative 1. And notice that 0, negative 1 is right here since we're counting by ones every tick mark. So 0, negative 1 puts me right here. And they want us to sketch the solution curve through that point. So again, if we're playing like ping pong with these, it looks like it's going to follow this down this way. Look how steep those lines are. So yeah, I think it's going to follow it down that way. And it's going to come up this way. Notice how steep these lines are. We're still kind of going this way. Notice that they get a little less steep, a little less steep. Oh, and then they turn around. We come back down this way and follow that. So I think it looks something like that. Ew, such an ugly graph, but you guys get the point. It looks something like that, which kind of looks to me like a parabola. So maybe this is the equation of something parabolic. Who knows? Although I guess it comes back up over here. So if we kept following this down, eventually it would come back up. So maybe it's not a parabola. Since it has a cosine, it's probably a trig function. Let's go. So there's my solution curve through the point 0, 1. No, it's not. Oh my gosh. Obviously you can tell I'm tired. I've been making too many of these videos. That's the solution curve through the point 0, negative 1. Oh my goodness gracious. I'm so sorry if you followed along with that. Let's try that again. Here's the solution curve through the point 0, 1. So again, follow your little pinball. Looks like it goes up somewhere that way. And then follow it this way. Kind of following along this way. And then the pinball shoots off this way. It doesn't have to be perfect. Okay, so now obviously it looks more like a trig function. It didn't look very much like a trig function down there at 0, negative 1. So, my bad. This is the solution curve through the point 0, 1. Part B says, write the equation of the tangent line to the solution curve at the point 0, 1. Remember, we need a slope and we need a point. So my point is 0, 1. My slope, if I plug in 0, 1 here, 0 for x and 1 for y. Cosine of 0 is equal to 1. And if I plug in 1 for y, I get 3 minus 1, which is equal to 2. So this is 2 times 1, which is equal to 2. So if I write the equation of that tangent line, that would be y minus y1 equals the slope times x minus x1. And then they want us to use that equation of the tangent line to approximate f of 0.2. So if I plug in 0.2 to this function, y minus 1 equals 2 times 0.2 minus 0, which is y minus 1 equals 2 times 0.2. Y minus 1 equals 0.4. And if we add 1, we get y equals 1 plus 0.4, which is 1.4. All right, so the approximate value of 0.2 on the graph is 1.4. And last but not least, it says let y equal f of x be the particular solution to the differential equation with the initial condition f of 0 equals 1. Find that particular solution. So, step 1, separate the variables. The 3 minus y needs to be moved over to this side, so I'm going to divide the 3 minus y over there on the left, and then dx needs to be multiplied. So this is 1 over 3 minus y dy is equal to cosine of x dx. So we need to integrate both sides. The integral of cosine is sine, so this is sine of x plus c. The integral of 1 over 3 minus y is a u substitution. So we have u equal to 3 minus y. du is equal to negative y dy. Sorry, negative 1 dy. And I don't want that negative anywhere over here, so I'm going to get rid of it by moving it to the other side. So negative du equals dy. If I actually do that substitution, that would be the integral of 1 over u du, which is negative ln of the absolute value of u. And if I replace u back with what it equals, that would be negative ln of the absolute value of 3 minus y equals sine of x plus c. Now, notice, by the way, again, it didn't change too much. We knew it was ln still, but that negative in front came from the fact that that was a negative in front of the y. Let's plug in our initial condition to find c. So my initial condition is 0, 1. So everywhere I see an x, I'm plugging in 0. Everywhere I see a y, I'm plugging in 1. So this is ln of 3 minus 1, which is ln of 2, is equal to sine of 0 plus c. Sine of 0 is 0, so c is equal to negative ln of 2. Plug that back in here. And let's rewrite this. So we have negative ln of the absolute value of 3 minus y is equal to sine of x minus ln of 2. Okay, and now we need to go forward and solve for y. So get rid of the negative first by dividing on both sides. Ln of the absolute value of 3 minus y is equal to negative sine of x plus ln of 2. To get rid of the natural log, let's raise both sides to the power of e. So we get the absolute value of 3 minus y equals e to the negative sine of x plus ln of 2. Now remember that property of exponents where we said if we're adding two things in the exponent, we can separate them and multiply. So this is e to the negative sine of x times e to the ln of 2. So let me rewrite that now. E to the negative sine of x times e to the ln of 2 is equal to the absolute value of 3 minus y. Well, e to the ln of 2 can simplify to just 2. So this is the same thing as e to the negative sine of x times 2. And I'm going to write that 2 in front. So it's the same thing as 2e to the negative sine of x. Three minus y. All right. Now, here's where we need to decide whether or not we need this absolute value, because in order to get rid of the absolute value, we have to make a decision about our initial condition. So, my decision is, if I plug in this point 0 and I want to get out 1, let's see what happens. If I plug in 0 here, sine of 0 is 0, so this is e to the 0, which is 1, and that's 2. If I plug in 1 on this side, I get 3 minus 1, which is 2. So the absolute value of 2 is equal to 2. So my question is, did I need to, what I would call that like utilize, or did I need to use the absolute value in order to get what it should have been? And the answer is no. This didn't create a negative 2 inside of here. So since this wasn't a negative 2 and this was always a positive 2, I didn't need the absolute value to begin with, so we can actually just get rid of the absolute value at this point. So we get 3 minus y is equal to 2e to the negative sine of x. If you did need to utilize that absolute value, by the way, if it required that you used the absolute value to get that positive 2 out, then what you would do, is you would make this side a negative number. All right, so last thing we need to do to isolate y, we need to get 3 over to the other side by subtracting it and then divide by the negative last but not least. So if we subtract the 3, we get negative y is equal to 2e to the negative sine of x minus 3. and then divide by that negative 1 in front of the y to get y equals negative 2 e to the negative sine of x, and then plus 3. And that is our final answer for our particular solution. All right, that was a lot of work for that one, but that was our last example for today.